Okay, in this lecture we're going to pick up where we left off in Chapter 3 and finish up the chapter. So the next section we need to talk about is 3.2.3.1. It's talking about RSTP. The STP, of course, stands for Spanning Tree Protocol. The R stands for rapid. And when they talk about rapid, they mean how quickly it converges, or the fact that it converges quicker than normal spanning tree that we had been talking about. And one way we accomplish this is that we have no port that is blocking, but we define new port states. And those states are first discarding. This should be the status for an alternate port, which normally before we would have blocked. So what it's going to do is throw traffic away. The port can also be in a learning state, which means it's listening for and processing the bridge protocol data units. And then the third state they talk about is forwarding. In the forwarding state, the port is still processing bridge PDUs and updates its MAC table accordingly with the frames it receives, and it is also forwarding user traffic through that port. Now then, on the next page, we'll talk about what the bridge PDU looks like. So it has a little more information. Here we have things like the protocol, the version, the type of frame, the root ID, the root cost, etc. As we go down through here, we've talked about, I think, all of these before. In the flags, they kind of explode that out and tell whether or not it's a topology change, what is the purpose of the frame, what is the port role, so the alternate or backup, root port, unknown, that type of thing, whether it's learning, whether it's forwarding, and whether or not it's acknowledging a topology change. Here they talk about something called edge ports, and basically what edge ports are switches that will never, or switch ports that will never be connected to another switch. So if this is our topology and we're not anticipating any change, these three ports are connected to PCs, this port is connected to a router. So they're all considered edge ports. Up here on these four connections, all of those are connected to a switch on both ends. In rapid spanning tree protocol, edge ports should immediately go into a forwarding state. So they don't really need to learn anything. They can immediately pass traffic to, in this case, switch 2, the 3 PCs, or in the case of switch 4, down to the router. This can be configured using the iOS command spanning tree space port fast. So basically what the port fast means is the port's going into its state as quickly as possible without having to wait for any BPDUs to come around. Using that command, the port fast command, that switches us from using normal STP, spanning tree protocol, to using rapid spanning tree protocol. In figure 2 here, they're talking about the types of connections. So port to port, which is shown here, will be in full duplex. If a port is shared, then it is connected to a hub, and therefore in half duplex. Okay, actually this is where we want to talk about that. So we have a bunch of port-to-port connections, but here we have a hub, and hubs operate in half duplex. So this link would be a shared link type because it's half duplex, and this would be a shared link type. If we connect them, click on all these others, they're going to be point-to-point because they do not involve a hub. Okay. This is an activity to make sure you understand some of the things that we talked about in this section. You can do this on your own. Okay, moving on to 3.3. They're going to talk about a Catalyst 2960, a very popular switch. And they're going to talk about some of the default settings. Of course, we can change these if needed. So they can be in enabled state on VLAN 1. It can be using per VLAN spanning tree, or it can be using rapid per VLAN spanning tree. Or actually, I'm sorry, it uses normal spanning tree. Rapid and MSTP are both turned off. The default port priority is 128. These are costs that we saw last lecture. So a gig connection has a spanning tree port cost by default of 4. And in the case of choosing a path, we use the lowest priority value. So the faster connection is typically going to have the lower port cost. Spanning tree VLAN priority set to 128. Here's the cost, the same as we have up here. And then we have those 4 timers we were talking about, the hello time, the forward delay time, the maximum aging time, and the hold count. Now then, there's a couple of methods for configuring the bridge ID. We talked about the bridge ID last time, which is what's used to determine who is the root switch. So method 1 is to force the device, in this case switch 1, to be the root bridge. Also down here we've gone in and we specified that for VLAN 1, S2 is a secondary root bridge if you desire. You don't have to do that. And the second method is to set the switch to a specific priority. In this case, this is about 15,000 less than the default priority. So, we can set this down lower if we know this is going to be the lowest value, and force, in this case, S3 to become the default bridge. Okay, here we're looking at, I think we've seen this before, the show spanning tree command. You have to be in enable mode, which we can tell from the prompt that we are. And it tells you the information about the root ID and the bridge ID and what interfaces we have. And in this case, Fast Ethernet 0/1 and /2, 2 different ports are both in port-to-port mode. And the third figure is one of the activities. I think this is the first time we've seen it in Cisco 3, but you should have experienced it in Cisco 1 and 2, where you can go through, it tells you what you want to do, and then you issue the command. These will be commands that we saw previously in this section. Or you can have it go through and help you step by step with what commands you want to do, or you can say, just show me everything. Which would be all the commands that we had previously seen in this section. Okay, this is talking about port fast and the bridge protocol data unit guard. Basically what happens is on a switch, ports that are not connected to other switches, we declare that they're port fast. We talked about that a moment ago. A port fast port should never receive BPDUs. If a port fast port does receive a BPDU, the BPDU guard puts that state in an error disabled state because that should never happen. They don't need to see or process the spanning tree protocol packets. So if we want to turn that on, here's the command to do that. We set it to port fast, and then we enable BPDU guard right there. Once we do that, if we want to look at the information, we can look at the port configuration. We can go in and say, show me the running config for a particular interface, and it will tell you that in this case, Fast Ethernet 0/11 has spanning tree port fast on and has BPDU guard enabled as well. So we can just go back. or maybe we're logging into a switch and we're pretty sure this is the way it should be set, but we want to double check it. Figure 4 in this section is another one of those activities to make sure you can remember the commands and how you enter them. It's intended for you to type here, but again, if you need help, you can do the show me, and it will show you what commands to issue. Okay, per VLAN spanning tree does support multiple VLANs. That's what the VP per VLAN implies. Don't know if we've seen this yet this semester. Don't know if we saw it previous semesters, but N802.1q trunk is just basically a connection that is capable of supporting multiple VLANs. When we have a VLAN and we're doing spanning tree, we have to have an instance of the spanning tree running, which is basically a process. So what they're talking about here is load balancing. And if you put all of your spanning tree algorithm calculations on one switch, that switch is going to be much busier than probably any other switch in the topology. So what they're showing you here is they have made the primary bridge for VLAN 10 to be S1 and the primary root bridge for VLAN 20 to be S3. So that distributes out the workload or the processing that is required of keeping track of the spanning tree protocol for multiple VLANs. So that's the discussion of this figure. If we go to figure 2, it's just going to show you the commands for root and secondary for both VLANs. So here we're making S3 the primary for VLAN 20. That's the command to do this. We're making S3 a secondary root for VLAN 10. Then we're setting S1 to be primary for VLAN 10 and making it secondary for VLAN 20. So that's what those 4 commands do. By setting their priorities really low, this is going to force the switches to become primary for their particular VLAN. Here we're going to say on switch 1 to show the spanning tree protocol or the active spanning tree configuration, and it's showing this for switch 1. Here we're going through and looking at relevant things from the running config. So notice there's some output enabled in this show running config, but as far as the spanning tree, it tells that we're using per VLAN spanning tree. We're using the extended system ID that we talked about in the last lecture, and we're setting the priority lower than the default, especially for VLAN 10, to force that to become the primary S1 for VLAN 10. Okay, 3315 is a packet tracer activity having you configure the per port spanning tree. I am going to assign that. It's relatively short. It's basically 2.5 pages, but look for that to show up in Blackboard as an assignment due in a week or so. Okay, 3321 is talking about the spanning tree mode. This is, I think, the same topology that we saw before. Notice that we're talking about VLAN 10 is the green dashes. VLAN 20 is showing traffic for in the dots. So all these trunks are passing, in this case, information for the 2 VLANs that we're talking about, VLAN 10 and VLAN 20. The second figure has some of the commands that we need for rapid per port spanning tree. Of course, when we're going to configure things, we go in enable mode, which is not shown. and then we do a configure terminal, or what I like to type is config T. Will put us in that. We then go into spanning tree mode, and we tell the mode is rapid per VLAN spanning tree. We then give the interface on the switch that we're interested in, and then we tell what type of port it is. In this case, it's a point-to-point. So we go in and say spanning tree link type point-to-point. And then we want to clear all the detected protocols. So we're kind of starting from scratch with rapid per VLAN spanning tree. So these are just the commands we saw in figure 2, but they're actually going in, showing you doing it on a switch and showing the different modes that you are in when you issue these commands. In this case, we're on switch 1, so we're showing the information about that. And then finally on 5, we're showing it for S1. Again, so we're going in and looking at the commands from show run. This is a packet tracer talking about configuring rapid per VLAN spanning tree. I'm going to assign this one as well. It also is about 2.5 pages, so not terribly long. When we go to 3323, this is a lab talking about rapid spanning tree and port fast and the bridge protocol data units. Labs are typically intended for doing on physical equipment. I think you should read this and pay particular attention to the output shown in the assignment labeled step 3B, which is on page 5 of the assignment. And basically it shows you the output the switch gets as it's going through and dealing with a change that has been sent in a BPDU. So it's kind of important. I'm not going to assign this, but like I said, you should read over it, especially paying close attention to that. Sometimes these labs we can do on the NetLab. I don't think this is probably a good candidate for that, so just read over it. Okay, how do you go about analyzing the spanning tree topology? So I kind of view this as you're working on a switch for the first time. You want to know some information about the switch, particularly related to is it running a spanning tree protocol or not. So I've had to do this before. I had to go into a bank one time, and their IT person was fired, and as a result, left immediately and would not answer any information about anything about the system, wouldn't give them passwords, that type of thing. So I had to go into, at that point in time, the 2 bank locations, the main branch, or the main location and a branch, and basically figure out their network. So, they pointed at it and said, okay, here's a stack of switches and routers, and over at the other location, we have the same thing. So the first thing I had to do is, break into the switch and set a new password. After I did that, usually when you have a stack switch, there's a bunch of cables, and it can be difficult and possibly inaccurate just to go through and try to do this. So what I did is I started with the top switch. I logged in, and I said show CDP neighbors. This is a command you should know from previous Cisco classes, but basically that shows you the routers and switches that are connected to the device you're on. So in that case, you're discovering the layer 1 and layer 2 topology. You can then go through and issue the show spanning tree VLANs to find out what VLANs you have, and then it has spanning tree protocol. And then you want to confirm that path in the output of that. So you just basically have to go through switch by switch and do that. If you're trying to draw the whole topology, There may be some things other than this you have to do, but again, the name of this graphic was analyzing the spanning tree protocol topology. So that's what this is related to. Okay, this graphic, we would have the root bridge, and this is what's called the expected topology. You know, do you have a root bridge? Does it have ports that are connected to other devices and are redundant paths or alternate paths blocked, so that we don't have all those bad things happening like broadcast storms or a unicast packet showing up twice, things we talked about in the first part of this chapter. Okay, so if we go in and say show the spanning tree for VLAN 100, it's going to go through and tell us, in this case for switch 1, what are the 3 ports, what interfaces are they on, are they forwarding, they're point-to-point, and then it will give us some of those timers. And it looks like all these are set to the default. And it will tell you the bridge priority and the system ID or extended system ID. Okay, what happens if we have a spanning tree failure? So we have basically the same diagram we were looking at before, but we have priorities, so we can see the priorities. We can also see the MAC addresses if we need those. So in the second figure, what happens is for some reason this point-to-point link has the block on it has disappeared. So we will have erroneous transmissions going to and coming from S4. And what this does is this can create a loop where packets just propagate around, if it's a broadcast loop, indefinitely, which is what they're trying to show here. And that is going to cause problems with switch 1, switch 2, and switch 4 because of that loop. So what happens if one of those bad loop things happen? Well, because it was due to a configuration error, what you would do is you would log into the incorrectly configured device, which in this case is S4, and you would set this port to be a blocking port. So in an ideal world, you would never have to do this. But if you do have a problem, you can just log into the switch and fix that problem, and then the packets will stop looping. Okay, this is an activity asking different questions. You know, what is the 15 seconds, or you know, whether this is switch 1, switch 2, that type of thing. Notice there are 3 different activities shown here. Sometimes the box is over here on the right to do your answer in. It's the case with the first 2. The third one are link information, you know, which one of these is blocking, or which ones are blocking in this case. So you can do that on your own. That's activity 3336. Okay, what we're going to talk about in 334 is what's called switch stacking. So I don't know if you've ever thought about this or ever seen it. Those of you that had 161 or Cisco 2 in the Newtown classroom building in room 206. But a lot of times the switches are connected like this. You know, you have a cable to switch above it, another port to switch above it, etc. And then you have a loop from the top down to the bottom. And this is called switch stacking. And this allows the switch to connect to each other. There's a protocol called switch or stackwise ports. These are ports over here that take a specific cable, and through the stackwise ports you build this stack. This stack has 4 switches in it. Obviously, you can stack up to 9 switches together using stackwise. One of the switches in the stack is called the stack master, and it controls the whole stack. and each stack member has its own unique stack member number. What happens is, from the standpoint of spanning tree protocol, which is what we're talking about in this class, this is going to appear as one switch. And there's some advantages about that we will see in a moment. In switch 2, here's a command, show running config, show me everything that begins with the word interface. I don't know how familiar you are with Linux or Unix, but this is very similar to the grep command. That is, take the output of show running -config, pipe it into something else, and in this case it is begin, which only looks for words or that begin with interface. So it's going to show you that this is, let's say, the bottom switch 1/0. So you have ports 1, 2, and 3, and then here's a couple of gigabit interfaces on the switch. So we're actually using more of the 3 sets of numbers, number/number/number, and that's because we have a stack configuration. So this grep or begin, whatever you want to call it, is very, very handy when you're looking at output, especially when there's going to be lots of output that you don't really care about at this point in time. So a couple of things here. It starts out saying diameter. So the spanning tree protocol diameter is the maximum number of switches that data must cross to connect to any switches in the stack, or all others. So you look at all the basically hop counts to get to every location, to every other location, and whatever the largest number is your stack diameter. So what happens is each of these stacks, even though if we have 4 stacks like we saw before, here's switch 1, here's switch 2, here's switch 3. And from the standpoint of spanning tree protocol, it is only going to talk to the stack master. So this helps us keep our diameter a little smaller, which is a good thing as far as convergence of the network and that type of thing. If we look at figure 2, in regards to what we have here, like I said, they've highlighted this, and each, I guess, yellow brownish rectangle is considered a single switch. Okay, the next page is an activity that asks you questions, true-false questions about some of the things related to switch stacking. You can do that on your own. 3411 is a class activity. Sometimes I assign these, sometimes I don't. For the time being, just read through this. It is possible I may come back at a later time and have us do this on the NetLab, but right now just read it. It's basically a page and a half, well, really just a little over a page, talking about switch documentation and something called a document tree. So you can look over that, and like I say, we may or may not see that in the future. So that takes us up to the summary, which is just basically summarizing everything we talked about in Chapter 3. So from a curriculum standpoint, we've covered all Chapter 3. I have some packet tracers and other activities that I assigned, some last lecture, some that will come from this lecture, so watch for those to appear in Blackboard. And also, I think Tim had mentioned to you something, a Project 1 that related to spanning tree protocol. So I will be putting that out on Blackboard with instructions as well. Also, since we finished Chapter 3, we will be taking the Chapter 3 quiz or exam in netacad.com. So watch for an announcement about that as well.